Thank you again. It's really great to be here, and then thanks for the invitation. I see that math is very unique when you want to do data science and approach data science. So there are not many math students out there who are doing data science. Very rare. I mean, currently in our company we don't have anyone who had a major in math. Previously when I worked at Mastercard and then Schnucks, we didn't have math major, and the closest, like some of them are statistics major, so really rare out there in the industry. But what I see is that we do have a very unique perspective if you are good at math and then took at least the kind of undergraduate in math. So I will try to share my perspective. So my title was that I was thinking about it, and title was data science from a math perspective. So I really want to share that. So what I will not do is I will not tell you what machine learning is. I will not try to introduce a lot of the concepts, but I will try to talk about some of the math concepts. Hopefully they make sense, because I found that it's very different when we approach problems. And then because of those training, because of those concepts that when you learn that is from a totally different perspective from any other department. So that's the perspective I will talk about it. I just want to talk about it. In the beginning, if something doesn't make sense, it's fine. But I'll try to make sure that I can share this and make sure that I try my best to make sure this is helpful to at least some of you. Yeah. All right, I'm gonna share my screen. Okay. So I also want this to be more like interactive. So I will ask questions throughout the presentation. And if you have any question, feel free to raise your hand, and then we can definitely answer questions as well, so that this can be more interactive. Okay. All right. So I want to start with some questions. So first question, if you're deciding if you're a farmer, deciding which seed product to purchase for my next year, which this happens typically after your harvest, which is could be October, and then in November, or you want to get a seed purchase before holiday, basically. So how do you predict this yield based on your soil condition of the field? So how do you know which one is better for my field, right? So, and then as a data scientist or mathematician, how do you solve this problem? So that's a question. What kind of data do you need? How many years of data? Do I need this seed product in how many fields? How do I analyze it so that I can make that prediction a little bit more accurate, so that I know that, okay, this product is better than the other product, right? So that's one very specific problem in agriculture. And then that's what I work at Monsanto for 4 years. So that's one of the specific problems they're trying to solve. Second, which item should you put on a printed ad, and what kind of deal should be associated with? So if you go to a store, typically whether it's Costco, or if you go to Schnucks, or any retail store, as of now, they have a printed ad that you can take a look, right? And then they have promoted items there. And then as a mathematician, you can ask yourself, okay, how do I decide which items to be put there? And then why should it be put there? What's the offer I should put? And then why? And then so you can ask that question, and then again, what kind of data I need, and how do I estimate if I put it there versus not putting there, the difference, and so on and so forth, right? So that's another question. Third question, how do you, let me, give me a second, I got a message.
I think Rudy said A/B testing.
Okay, A/B testing. Yeah, A/B testing is good, right? I have another screen. I will make sure I can read your comment. Okay. So yeah, A/B testing is a good one, right? So and then fundamentally, then how do you measure the success? A/B testing is widely used in marketing campaign in retailer. So that's basically for every concept that you want to test, then it's through A/B testing, which is definitely the way to go. Yeah. But analytically, mathematically, how do you model it? How do you know that predictively, say next week, what should you do? Even before you test it, right? So what should you do? From a model, you know, okay, you need to promote this at this price. You need to promote this at this price. Which combination? Should I have a seafood and a produce combination or different? What's the percentage that I need to promote, and so on and so forth. So, and why? And is there a difference, or I just randomly pick something that I care about and then put it there? Then I'm done. Or let the artists do the job, make it beautiful, right? Looking really nice, then it do the job, right? And so on and so forth. So, and that's another question. How do you detect and block a fraud transaction almost every time? So that's a question that Mastercard is answering, that whenever you use your credit card and then to make a payment, there is a model that's being run every time. Whenever there is a transaction, it will analyze your historical data, your transaction history, and then make a inference that whether this is a fraud or not. And that's why you get a lot of sometimes blocks when you don't want them to block, right? So I'll ask some questions around that later. So the first one is the hot topic. So if you are reading a book or if a digital book, right, and then you want to use the most recent technology, generative AI, to return answers from a book. If you have a book, if you're reading Harry Potter series, and then you want to develop your model, which combines a large language model, which is the, ChatGPT is one of them. You can use their base model and then combine with your data set and then return the answers from your data that you have. If you are writing something, then it can actually summarize what you want. So that's possible. So how do you do it, right? So that's another question. So what's possible? What's not possible? What does it take? What's the cost, and so on and so forth. So generative AI and large language model are the hardest topic in data science as of now. Yeah. All right. So just want to start with some questions. So those are the real world questions that can be answered. So I was directly involved in this one, and somewhat involved in the third one, and then the fourth one also I know what it takes to do. So those are the questions in the real world that can be answered, and there are tons of questions that can be answered by using math and then the data science, which is built upon the math. So. All right, so moving on. What is data science? So I'm not going to give you the definition, but this is typically what data science folks use to describe data science. So data science is three things. So first one is math and stats. And the second one, they call this hacking skills. You can also call it engineering skills, which is the coding and all those kind of things. Coding and then SQL or Python, R, and so on and so forth. And then the intersect of math and hacking skills is called machine learning. So that's where data science is really from, right? So it's the key difference is when machine learning becomes more and more popular, then data science become more like a subject. And then the third one is the this one is in substantive expertise, or we also call this domain expertise. So if you only know coding, and then if you don't have any math, and then you work on a domain, so that's what they call this danger zone, right? So because your inference might be inaccurate because you don't understand distribution, you don't understand the math, you don't anything. So anything you got could be a random noise effect, and then you call that this is the conclusion. That's actually a lot of the business folks. They're kind of here. They are not even using hacking skills. They're just using their business skills and then plus Excel and then try to do something, right? So that's what a lot of people stay here. Math stats and domain, this is traditional research where there is no machine learning. So this is really good as well. A lot of papers around it, right? So this is where, and then data science, what they call this is in the middle. It's a combination of hacking, math, and domain knowledge. So This is typically how people talk about it, but that's when they don't talk to math students, right? So I'm talking to a math student, math group. So of course we need to make some changes here. So I'm making some changes, right? So not on the slide, I'll talk through this. So I've been working with a lot of students. So there are students from hacking skills, which is basically they have a major in engineering in computer science. Of course, there is always mixed, right? So it's a focus. So there are majors that have a more focus on hacking skills, and there are majors, even like a math program, we learn coding as well, right? But not as the level as computer science major, because that's what they do. And then they have many courses around it, but we also learn programming languages. So I have opportunity working with math students, not a lot of math, stat students, a lot of business students, which is from here, some engineering, like quite a lot of engineering students, kind of electrical engineering, biomedical engineering, industrial engineering, and so on. And then what I see that is learning computer science, learning programming language is much easier at work. And learning domain knowledge, it's also easy. Sometimes it's hard for some people if they really don't know how to ask questions. This becomes a challenge. But the most challenging part, if you want to learn at work, is math and stats. That's where a lot of data scientists in the industry are lacking, is the fundamental math and stats understanding. And then that, because of the lack of knowledge in this area, and then when we actually work on data science problems, then you always feel that it's not that deep. The questions, we're asking questions, but then when I work with some students, then they're not asking that question very deep, from a very deep perspective. And then it's kind of a staying on the surface and then don't understand the essential part of the problem. So that's where I see that math and stats play a huge role. Of course, you can still learn at work and you can take some courses, but it takes a lot of effort to go and learn math and stats again. So that's the real the thing I really want to talk about. And also here it says it's machine learning, right? So when you combine coding and math stats, then you get machine learning. But actually there are more. And machine learning, I even put the statistical modeling here rather than the traditional research, because statistical modeling is also evolving. As long as you introduce certain predictive component into your statistical modeling, then it becomes a machine learning. So the boundary is not that clear. And then there's also optimization, which is there as well, which also involves coding and so forth. So there are techniques that are beyond machine learning, and I'll talk about it and then introduce some difference across this kind of techniques. And then I think in a couple of slides. Yeah. All right. Okay, so I did ask whether this group, everybody knows machine learning. So my answer, the answer I got is probably not everyone. So very quick, right? So machine learning is very, very easy to understand. So this is some kind of figure I found online. So you have an input, which is raw data, and then you build an algorithm which divides your data into a training and your training data set, and then there is another data set which is the validation. So you train your algorithm using training data, and then you compare with whether the desired output, and then try to learn the supervisor. Basically is a learned model based on the output, and then learn an algorithm that can map your training data set to the desired output. So that's the machine, and then you also validate it. So and then when you have a input that's new, and then you plug it into the model, which is essentially a function. Now I'll introduce that very soon. And then you get an output, and then the output is an apple. So the core of the machine learning is really that there is a training and that there's a testing, so that you know that the algorithm that you develop can work on some data that it has not seen. Okay, very quick. So fundamental of all this, any of this modeling technique is actually very straightforward. It's actually just the y equal to fx. And then every method is doing the same thing. It's trying to minimize the loss function that's defined based on the outcome, and then the function, and then the input. Of course, this. So this is basically everything, the fundamental. So not everyone, however, understands kind of thinks about problems from this perspective, because math students are trained a lot using the kind of in even simple like a function and then all those kind of notation and all those kind of training. So it becomes very natural for actually a math student to think about problems like this. So when you minimize the loss function, so if you try to your output is the function, which means you have an input, like the previous example, you have images, and then you know the label, which is whether it's an apple or an orange. Then you can use that, which is your y, right? So that's an apple or orange, and then x is your images. So and then you train a function, then that's your machine learning model, or you sometimes it's also statistical model. The boundary between machine learning and statistic model is very it's not really not clear at all. So so if you learn this, if you have a data and then you try to find the mapping, then that's machine learning. And then you try to find a function that maps your data to the label correctly, and then also when new data come in, you can map them correctly as well. If you're after this x, which means that I know the function, I know the data, and then I'm trying to find the best of x, right? So then that's optimization, which is, I don't know how many of you have taken the linear programming class, right? So that's the minimize a loss function, and then such that a certain list of constraints are met. So, and then you try to find the best x, right? So that's optimization. So at the end, so the those three core modeling techniques, machine learning, statistics, optimization, at the end of the day, it's just this, you know. So that's the fundamental perspective that when I think about the problem, I think about like this. So it's really so that we can actually choose technique freely, because fundamentally they are the same. And then we choose the best technique to use based on the problems that, based on the specific problem, which method works the best for the specific problem. All right, quick example. This is the like a linear regression where you have a y equal to this, right? So I have a lot of data, and then what does this do? Linear regression, which is both a statistical model and a machine learning model. What does it do? Is just minimize this loss function across all your data. So that's what it does. So this is basically everywhere in machine learning. Linear regression business. Yeah, that's true. Yeah, so they like linear regression because it's so easy to understand and you can interpret very well. Some industry, the financial. So in fintech and any financial predictive model that's been developed need to be regulated. So they have to go through a model governance process, and whether your model can be explained is very important. So sometimes they just go back to a very basic model, such as a linear regression. Yeah. All right. So very quick. If you know machine learning, I'll just ignore this slide, right? So very quick. So machine learning, there's a supervised learning, which is y-axis is supervised versus unsupervised. Supervised means that you know that it's an apple or an orange. Unsupervised that you don't know. So you don't know the label, so you don't know what that is. It's just trying to differentiate your data into different groups. And then there is a discrete or a continuous. Discrete called classification, continuous called regression, and then this is unsupervised discrete dense clustering, unsupervised continuous dense dimension reduction, the PCA, and all those. So this is a basic understanding of it. And then supervised learning is that you divide your data, you know the labels. So this is a red and blue and green, and then you know the label. So you learn the model to differentiate them. And then if you run unsupervised learning, then you try to find the distance, for example, of your data points and try to find clusters, but you don't know the meaning of this group. What does this mean? There's no label. So that's the basic. I just want to introduce a little bit about machine learning so that you know what we're talking about here. Yeah. So at the end, your machine learning is really typically when people talk about machine learning, it's about supervised learning that you have label, which means that you have this Y and this X, and you're trying to get an F. If it's unsupervised, then you don't know the Y, you only know the X, you're trying to do the clustering. And then which is also an F, but that F separates your data into different groups. Yeah. So key differentiator of machine learning is the cross validation. So all it does is try to divide your data into training and testing, and the percentage. Sometimes they use 60-40. Sometimes they put another 10% as a holdout data set. And then you train and then pass and then minimize the loss function across data set, and you learn this F, and then you validate it by checking the loss function on this testing data. So that's everything it does. But once you have this framework, then when you work on machine learning, then there are a lot of details, right? What to do, what kind of models, and why, and then which technique is better, and so on and so forth. So what I'm going to talk about next slide is a quick comparison of these approaches. I'm going to spend a few minutes on this slide. It's a busy slide, just bear with me. So machine learning, statistical modeling, and optimization from a loss function perspective. Machine learning has a lot of different types of loss functions. It's not as standard as statistical modeling. Typically, the standard distribution related. Statistical modeling is always having those assumptions in mind, so that it knows this has specific distribution assumptions and then the theory around it, so that it defines the loss function around it. And then the loss function typically also need to make statistical sense. But machine learning, they just define however they want. So and then optimization is also the loss. There's really no loss function because we're this is the core of the formulation, is the objective of the optimization approach. Machine learning, there are mostly math-based, but there are a lot of IT-based approaches as well, a lot of iterative approaches, like the deep learning. When it learns, it's a lot of math-related, but it's really hard to interpret it from a statistical perspective. So there are a lot of algorithms out there for machine learning. And then statistical, of course, is distribution-based, statistical theory-based. And then optimization, then objective function and constraints, which is you minimize the objective function, satisfying specific constraints. And then convex, that your search space is convex, is extremely important. And then we almost have to stay at integer and linear, meaning that all your constraints should be linear, and then you can only have an integer in it. And then once you have quadratic, it becomes very hard to be solved. Yeah. An equal solution or not, this is something that maths always care about. Do I have a kind of a formula that I can solve this problem, right? So machine learning then typically know an equal solution. That's why this is sometimes it's really hard. So when people come up with a machine learning algorithm, typically the machine learning algorithm comes first, and then people start to explain it using statistics. But statistical modeling, sometimes, yes, there is an equal solution, and then optimization, there is no equal solution either. So this is really an optimization problem. Statistical explanation, that is the strength of statistical modeling. And then for machine learning, as I mentioned, sometimes no, especially for deep learning and then large language model, is a lot of engineering and IT and iterative solution and so on. So the deep neural network and a lot of calculations and then all our assumptions in it. So the most important thing that differentiate and why machine learning becomes the center of data science is this cross-validation. But if you really think about it, if you introduce cross-validation means means that you train your model on part of your data and validate it on another part. The statistical modeling, if you run a linear regression, is probably overfitted. And then any statistical modeling without cross-validation is going to be overfitted. Overfitted it just means that it works for the data that the model has seen. When the new data comes in, the model behaves really bad. So that's overfitted model. But if you really think about this, that if you introduce cross-validation into different modeling techniques, then the every model can be like a machine learning, because as long as you can cross-validate and then train and validate, then it is a machine learning, some type of machine learning model. So we have actually built models which is very much statistic based, but we still divide it into two, and then we train on one and then validate on the other. Make sure that the model validation performance is good, then that's a good model. So going back to the fundamentals. So there is no real difference between machine learning and other models as long as you fall under this cross-validation, right? So then that's called a machine learning, and it's trying to predict a data that it has not seen, and that's prediction. Yeah. All right. So far, any questions? I know it's a little bit dry, but I want to set up this context so that we can talk about something a little fun. All right.
So sorry. So for cross-validation, so it's mostly used for machine learning, but you can use it for any statistical modeling.
Yes.
Okay.
Yes,
okay.
exactly.
And the reason that you say the two of them are the boundary are sort of blurred is when you use cross-validation for statistical modeling.
Yes. Yeah. The boundary is not is kind of blur. Is one reason is that you can do cross validation. The other is that a lot of machine learning algorithms are statistical models. Yeah. So linear regression, it was a statistical model. It's not like it's used later for machine learning, right? And then yeah.
Thank you. So when the statistical model that was overfitted, then what would happen when you do the cross validation? So it will see that it's overfitted. Then usually what would
usually
do
you
next?
either go back to machine learning, or you introduce so there are specific steps when in machine learning world that when you see overfitted model, typically involves reduce the model complexity so that the model is not too low, kind of fitted to localized signals, right? So you reduce the model complexity, removing certain variables, making the model a little simpler. So you can use the same techniques when you fit a statistical modeling. And then so basically use the same technique of machine learning when you see an overfitted model, and then try to apply the same thing for statistical modeling, and then you can see the same result. Yeah. And then in machine learning, there are specific terms. You add regularizer terms, and then those kind of techniques, and then you can also do similar things. But what I see the most is that when people approach problems, they're approaching this as an either or. So they're approaching this typically when we fit a model, like a statistical model is trying to explain, right? So you fit a model is always, we're thinking about this as I fit a model to my data set, and then so this is the statistical model that explain my data set, but we're not thinking about, okay, so it explains this data set, does it explain for future data set, right? So then we need to have that concept in mind that you need to do a cross-validate. And that's the typical mistake when stats students, when they fit a statistical model, which is really cool, but then, okay, you don't cross-validate, then how can I use it? It doesn't work for new data. And however, sometimes when we were trying to, it depends on the problem we're trying to solve. Sometimes the predictive part is not part of the problem statement. Then statistical modeling which shine, and then you no longer need a cross validation.
Okay.
Yeah, and then same thing for same thing for optimization. If you consider optimization, it's the same thing. If you run an think about it. If you run an optimization and then which returns you a portfolio of stocks, right? And you need to validate it using the data that it has not seen. So if I use the data if I use 1 year of data to train and then get a portfolio of stocks that I believe that it performs the best from a risk perspective, from a return perspective for that year of data, then what's the performance for the next quarter? And that's cross validation. So it is everywhere. So you, as long as you, my point is that the techniques are there. The cross validation is a key that differentiate whether your model is predictive or not. So that's the real difference. Yeah.
Okay, thank you.
Yeah.
Could you also help people who weren't very familiar with these language to understand what does the overfitted model look like and why is an overfitting bad?
Yeah, so overfitting model is that if you is the most traditional example is that if you have a linearly related data points, right? So they're kind of scattered around a line, and then if you feed a higher order to that data set, then you start to learn not a linear, you start to learn this kind of zigzag, right? So, but that's not what the trend of the data is. The data is linear, and then you're learning something localized. So when you make a prediction, it's going to give you something weird, so that's an overfitted model. So basically what it means is that it works for the training data and doesn't work for the testing data. Yeah, it means that if you run a machine learning model and then you learn something from COVID period, you say, okay, Netflix is the best stock, right? And then if you don't validate, then everybody go and buy Netflix. Then it doesn't work anymore after COVID. And that's what it means. So okay, all right.
Thank you.
All right, so a few concepts. So now going back to the math, right? So this is the perspective I really want to talk about it, because this is how I see data science and how fundamentally when I talk to non-math students, when we talk, even this simple concept sometimes is not how people think. So for mathematicians, math students, this is how we can think about all those problems out there. At the end of the day, it's about the function, it's about the mapping, is about loss function, is about different models, is about the core technique, like cross validation, whether it's used or not, so it's about the fundamentals. It's only a few of them then help us understand the technical foundations of the data science. Yeah, of course the reality is that things are a little more complicated, and then we need to understand different machine learning models, what they are, what is a random forest, what is a logistic regression, and so on and so forth, right? So, and then what's the theory behind it, and so on. But I know that if you take the class, then you will know them. But this is just my perspective, and then I don't think you will see it very often, so out there. All right, a few concepts on how they're really math. This is the fun part. I did spend quite some time thinking through what kind of a concept is really interesting in math and how they are used. So what I'm going to do is that I will talk about the concept and then talk about my perspective, and then we'll talk about the example. Okay. So the first thing is linear algebra. So I know that some of you are junior, sophomore, right? So linear algebra is I think you have to learn that. So the linear algebra is basically the center is a matrix, right? So and then a matrix then is the center of everything in data science. Matrix is the center of coding. So if you know SQL, if you don't know, that's fine. So it's basically the database management programming language, which is a based on table. So databases are typically database we'll call a relational database, which is tables and the relationship across among tables. So that's what that is. So that then every computation is around the matrix. So having a good understanding of basic matrix manipulation, feel comfortable thinking like that is very important. And then and then coding, even in other programming languages, I used it when I was at school. I used MATLAB, and then whether you are now using the most popular is Python. Statisticians use R, right? So and then whether you use Python or R, the most important thing, the first thing you need to learn to do any data science is don't write too many for loops. Try to do everything, every data manipulation, everything in matrix. So the matrix thinking is really, really important. So this concept is really not that much about, okay, I'm gonna apply a lot of my learning in my linear algebra to data science if I will do data science in the future. It's about that training about the matrix. It's about that you're thinking like that. You know that, okay, I can do the, when you learn the linear algebra, you're gonna know the rank of a matrix and all those kind of things. That it becomes very intuitive to you, and then it's very abstract, but become very intuitive after the training. All right. Yeah, so that's the yes, that's the answer is yes. Yeah, so the localized effect, and then it will get very weird results. I wish I could have a visual. You can search it, overfitted linear regression, then you will see that. It's very there are a lot of visualization out there. So this is the first one. It's also core of the elimination problem formulation. It's also about matrix. It's the everywhere. Matrix is everywhere, and then the second one I talk about here is a linear transformation, which I will talk about again in I think a couple of slides. So this is the first concept, and this is the foundation. So I don't have a very specific example to talk about it. The second one, differential equation. This is one of the kind of a ordinary differential equation, partial differential equation. So it's a easy and hard, right? So and that's when I was in my undergraduate, I was learning the partial differential equation is so hard, So it's solving that kind of problem is really just sometimes painful. But what you get from this solving those differential equations become like derivative becomes a thing, the easy thing for math students. So anything around, so this is the quantum velocity features. When you make a fraud prediction, you need to know whether there is a significant change of behavior from that moment to the history, because that means something strange is happening. So that's velocity. What we call velocity is a change, right? Change is derivative. So change is derivative. Sometimes you need to have like a change of change, derivative. But if you don't have that training, then it becomes very abstract, and then people can't really understand and grasp that concept. And how do I think about it? How do I apply this in my problem? What does this really mean, right? And then a lot of students then start to kind of get confused on when we think about it. Sensitivity. So it should be sensitivity analysis. So which is what if analysis is once you have a model, what if this happens? So those are also kind of a changes. So that's also widely used also in model explanation. That's why linear regression is very popular, because you can explain the impact of each one, and then when there is a change, what's the impact on the overall outcome, and so on and so forth. Yeah. So one example. So it's about predicting sales. Once you build a model, right? So that can predict sales for a company, for example, for this week or for next week or for next quarter, right? So and then you can ask the question: what if the Fed raised interest rate one more time, right? So this is the hot topic. So it's keeping they're keeping it flat. And then what if they raise it one more time? What's the impact to my business based on the prediction? How should I incorporate this signal into it? So that's a change. What if Fed keep the interest rate? What if inflation reduces to 2%? Right now it's still above 3%. If it really reduces to 2%, does it hurt my business? Does it help my business? What does this mean from a sales perspective? What contributes to the sales this week? Why is the sales this week higher than last week? Why? What has changed, right? And then those are all changes. Whenever there is changes, it's about derivative. And then whenever there's derivative, it becomes a little bit abstract and then a little bit hard concept for real world data science to really grasp. And then so that's where learning that kind of course, when you actually take, so the actual like a differential equation talks about things much different from this. This is very kind of a easy part of that. But the real my point is that once you work on the hard part, then the easy part becomes more like your intuition. Like it's natural for you to think like that. It's really hard to describe it, but when we approach problems, this kind of a derivative thinking, and then it becomes very, very natural for math students. Yeah. All right, I'm gonna move on. Another questions. So, and the second one, the third one, abstract algebra. So there is a concept called quotient, right? So this is the I don't know how many of you are learning this, but I found this one specifically very useful in data science. I don't think anyone talks about this, but so quotient is in abstract algebra, and then I mean the easy understanding is that you have your integer and then you divide that into two groups, which is even and odd integers, and then it's like a quotient. It's the this is I basically copy paste from Wikipedia, right? So and then you do that quotient. So and then we learn it in a very abstract way. You have a group, and then you have a subgroup, and then you do a group divided by the subgroup, and then that's how you get a quotient, right? So and then we learn that, okay, all the manipulations around it and how to do that, and then the properties of that, and so on and so forth. But then so this becomes again very natural for math students. And then the question is, why is quotient measuring something different? So actually in business, this is a very important concept. The specific in machine learning it's called normalization. One example is that you in the yield prediction, when instead of considering the raw yield, you do the raw yield minus the average yield of 2022, which is the simplest example of a quotient concept. That is, you are trying to remove a fact, you're trying to remove a fact in a way that is normalized. So there is this normalization concept is almost the same as the quotient concept, but it's not as rigorous as the quotient because there is a definition, everything around it. But that kind of training actually help you understand, okay, everything can be divided by another thing, and then define a normalization. And it's very hard when I was trying to explain this to many students or some of the other data scientists I work with. Okay, this is why you need normalization. And this is, whenever you think about when you define the variables for prediction, you need to think about normalization. And there are tons of ways to normalize. You normalize against this effect, against this effect. And then why am I thinking like that? Because we had a training about this, the abstract algebra, which is that thinking, it becomes very natural. You know that the data set, you don't have to work in that space. You can work on a different space because you can remove something. And then actually, instead of considering integer, you consider even number, odd number. Instead of consider 0, 1 to 5, you can consider only 3 groups, right? So this is the concept that when non-math students, when they think about, they're not going to think about like this way, right? Because it is too abstract for them. But actually, when you work on data science, this becomes a very important thing because normalization is a huge thing in data science. And then there are many, many, many examples out there that require you to remove effect and so on. All right. So predict yield, should I use raw historical yield to predict future yield? Given that, so if you don't know that actually weather dominates yield, so every year, why is the grower getting different yield is only because of weather. That's dominating, which means like 60 or 65% of the yield, whether you got high yield or low yield, is because of the weather. So maybe I should consider quotient space, normalize the yield against year, right? So that's one. Do I need to normalize against the mean owning or mean and variance, which is a practical problem? That's not a problem in math, but practically, should I normalize against the mean, meaning that I only minus the mean, or should I also remove the variance, which means divided by standard deviation, and so on and so forth? So that's the specific question you ask. Is there any other dominating effect that I need to remove? In some of the model that we build, we need to remove the field effect, which is another huge effect when you have multiple fields that you are working with, and then you need to somehow remove the field effect because you're trying to launch a product, and then you want that product to work for every field out there. So you want to remove that effect. So that is you're focusing only on the products that you're developing and so on and so forth. So, and then the thing here is that there are a lot of division that you need to consider. I'm talking about division from this quotient perspective. So that is the effect that you need to consider is very different. And then the math students can navigate through this concept very easily. Yeah, math students can navigate through this concept easily. But if you don't have this training, it's so hard. Yeah. All right, moving on. Real analysis measure space. So this is the another one, which is in actual data science problem, binary classification is almost the most important classification model out there, is predicting binary outcome, 0 and 1. And then probability is widely used. And then typically instead of predicting 0 and 1, a binary classification model typically outputs probability, which means and then you choose a cutoff, it's above 0.5, then I label as 1. If it's lower than 0.5, then it becomes 0. So this is another example that distributions everywhere, statistical assumptions are everywhere. But the real difference of a math student is that you are understanding this from a real analytics perspective, which is from this measure space, and then probability space is just one example of a measure space. And this is very unique. I can't tell like how unique it is, but it's very unique. And then your understanding of this is fundamental. You understand this in a very general way. And when we use it, you are not going to stick to the probability, because if you approach things just from a probability perspective, you are limited by probability. But when you think beyond probability, then you can navigate. You can pull out a probability to a different one. But you still know that that follows the same attributes because of this understanding of measure space, which is a generalization of a probability space. So that's another example. Example, fraud detection. What do you think the confidence of the model is when the transaction is blocked? I want to pause and ask, what do you think the confidence of the model is when the transaction is blocked? The likelihood of a transaction is fraud. Someone give me an answer.
Like maybe 80% or 90%.
Okay, not that good. Okay, it's the flip of 80%, 20%. So your transaction is blocked because the model thinks 20% chance you're a fraud. Okay, so that's the math. I think it's 25%, if I remember that correctly. 20 to 25%. It's 1 to 4.
Wow.
Yeah. Okay. Why is that? Yeah. Why is that? Yeah. Why is that? Right. So this is what makes the problem different, given that fraud themselves are like outliers of distribution. So if you're a stat student, then you know that there are so many data points, right? So only a very small percentage of fraud. So when you train a model, you are almost trying to identify those extremely outliers. And because of that, and then that's the reason why the model is so hard to get accurate on those small, really, really small data set, because the actual fraud versus non-fraud is definitely beyond 100 to 1. And whenever you have a data set that is called unbalanced data set is beyond 100 to 1, it's really hard to get a really nice false positive rate. Yeah, so that's the only reason. And then they're really doing really well. Like Mastercard has, they're doing really well. And then you need to think about then what kind of metrics makes more sense to measure the success. So that's another one, which is related to probability. You know, the probability is different when you are talking about the outlier and your distribution is highly unbalanced. So that's another one that related to the probability space. Okay, the last one. This cumulative diagram, I would say this is the most important thing in data science that in math that can be used in data science, which is, in this case, this is the G divided by kernel, right? So you think about this is the relationship. You are, instead of working on one space, you work on another space. Instead of working on so you have a function from A mapping to C, instead of working on A and C, you work on B and D. Or the vice versa. So this is the most important thing, I think, is this, because a lot of times when people think about solving the problem, they think about working in one space, but as a mathematician, you pour it to different space to be solved. I have a very specific example for you to understand. And then when I actually, for that specific example, then my team member then asked me, how did you come up with this idea? It's because of this, right? Then I can't explain, okay, because of the cumulative diagram. They would be, okay, what are you talking about, right? So then the example is a predicting raw or versus predicting relative normalized, which is around whether you do this divided by kernel or not. So you can think about this, which is instead of working on G and H, you work on this normalized version, which is divided by the kernel and the H. So that's one very simple example. And then, so this is the example. So we were predicting inventory outs. So inventory outs are outliers, right? So that's the, but we can't predict that in the same way as predicting frauds. I was designing this as a question because inventory outs, you don't know whether they are outs. Fraud, sometimes you know they are fraud. But inventory outs, you have to go to the actual store to see if they are out, and then okay, you confirm it's out to tell you okay, it's out. So I know that is out. So you don't really know the label here. So the question becomes, should I work on the distribution of sales, where when the sales is really low, then I say okay, it's out, or and stay at the sales space, or should I map it to different space to work with? And then specifically, I'm not going to go too much into detail because there is a pattern behind it. So the specifics around it is that we map this from a sales perspective to number of hours perspective. So instead of working on the actual sales, we work on the number of hours without sales. It's a small change, but the space you're working with is totally different. And then we have to map all the other variables to that space as well. And then you make that prediction, run the model using in this space. Everything becomes so much simpler. And then our false positive was like, our accuracy is like 60%. This one is 80, 98, 99% accurate. So that's the one of the specific example. All right, so last slide. Fundamental of data science is math. As I said, if you are interested in data science in the future or right now, I know we have teachers here. If you are talking to high school students, if they're interested, definitely math is the fundamental of data science. A lot of however, not many actually mathematicians out there doing this in this business. And then what I want to leave to everyone is that even sometimes even basic maths and advanced maths help you solve data science problems without barriers. Yeah, just want to end here. I know I'm didn't have any time for questions, but I can stay for a few minutes if you have questions.
Thank you so much for the talk. Let's thank our speaker first. All right. Do you have any questions?
So I guess regarding the idea from before of like, not really questions, like the other question from before about like switching spaces sort of. So like, is that basic? So is that like you're switching the categories in a sense?
Yes, so this one and this one, I think they are related. Switching space when you do the quotient, this is also related to switching spaces, but this one is a little bit more specific. It's focusing on the normalization. So whenever you divide something, it's one type of normalization. And then something important in business is that every division, like when we write in this way, need to have a business explanation. So we have to be very specific when you divide. Okay, what does this mean? What's this the new thing that you're measuring? So whenever we divide something, then we need to define, okay, this is what it's trying to measure now. And then, so this one is a little different, but that's the uniqueness of this one. But this is, yeah, as I said, this is the same as this part. Yeah, that's this one. This is basically you can think about this is divide, this is more like a quotient, and then this space doesn't change. So you work instead of the original one, so you remove an effect, which is the kernel. I mean, not exactly the kernel, but you divide it, you remove an effect, and then after that, you still work with the same space.
So I guess so basically you know that that if you can convert G to G divided by kernel, right?
Yeah.
And you know that I guess it's easier to work with G divided by kernel. And if you do so, you will get the same result.
Yes. Yes.
Okay.
Yes, exactly. So the example I was giving, that it is instead of working on the raw yield, you should consider relative yield. So which is a version of this. Is not exactly the same, but it's a version of this. So that's a much simpler problem. But actually, you're solving. It's almost the same. Yeah.
It's very interesting to see the application of abstract algebra in the data science. I have never thought about it that way. But I always tell my students that once you learn abstract algebra, you're going to see math from a different perspective. Math is going to be different for you, and it's so interesting to see the connection here.
Yeah, I hope that this is helpful. I mean, I never talk about this to anyone, so it's really new content, first time presentation. So
I had a question.
Uh-huh.
You mentioned at one point that when it comes to data science, you would want to avoid using for loops.
Yes.
And instead implement or utilize the existence of matrices.
Yes.
Is that something you could explain a little bit more, or do you think that's kind of...
This is called a vectorized coding, which is that you don't want to do for loops because if you can turn your computation into a matrix, then the coding time becomes much shorter. And also for certain programming languages, if you do a for loop, even for Python, the speed becomes very slow because of how it utilizes memory. If you use some of the fundamental programming languages, C++, Java, then they can handle for loop really fast. But if you try to do in R, do a for, and then just I equal to I plus 1 for a billion times, it will get stuck, so because of how they render the memory. So avoiding for loop is almost the most important thing in coding. And then using the matrix and do table joins, left join, and then do aggregation using matrix, and then that makes your implementation much faster. Sometimes when you write a for loop, you have to write 10 lines of code, but sometimes when you use a matrix, it's 1 line. So that's a huge difference. And from a speed perspective, for certain programming language, when you use for loop, it becomes much slower. And then what I want to always help my data scientists understand is that your time needs to be spent on solving the problems. It's not spent on coding. You need to ask questions and implement and test your assumptions quickly, not to spend a lot of time writing 1,000 lines of code. There was one senior data scientist I worked with who didn't learn this. And then he spent literally 1,000 lines of code to solve one thing. And then we said, okay, you should just write a few lines of code and you can solve it. Yeah.
Well, thank you.
Yeah, sure.
I have a question following from that.
Mm-hmm.
So I'm not like really particularly sure about this, but like for example, could this be like this sort of implementation be like so like if you had like a list of numbers and you wanted to increase like each number in the list by like a certain value, like 1, like a set value, could you like if you're using this approach, instead of like using a for loop and for each number a for loop going through each number and just adding 1 to each number. Instead, you represent the numbers in the list as like a vector, and then you add that with another vector that's like with like a bunch of 1s. Would that be like sort of like how this approach would work, kind of?
Yes. So there are specific problems. That example was trying to explain that the speed is very slow is how they because R or Python I think Python is much faster. If you do that, you can try it in R because everything in R is more like a data frame. So and then the memory usage is very bad, right? So you can then change that. This is what we call a vectorize everything you're doing. So that's like for that specific example, it doesn't exist. We never have a need to just do a I plus 1 for a billion times. So there's no real world example of it. But there are many examples out there that you need to vectorize, and then even for like some of the matrix. That's what I was saying, that in one of the application is that matrix thinking. Sometimes you need to do a multiplication of matrix to achieve something. Yeah, sometimes it's define another vector and multiply that by to that matrix, or because then it becomes a much faster. Yeah, so that's about this matrix. You go here. Yeah, sometimes you even need to do this X transpose A times X, because it is really fast to get a constant, right? So and then this is the way to do, and then. Sometimes it's A times X, but sometimes, in many cases, it's not about the multiplication. It's about formulate your problems in the vector or in the matrix so that you can utilize the matrix thinking, and then which is a much faster, easy implementation. And specifically, that every data that we are working with are in database. Almost all of it, if you go and then in the industry, almost every data you get originate from a database, and then database is a matrix design. So you have to start to work on matrix data. It's not, yeah. So and then, yeah. So go ahead. Yeah. I think it will be the ON, and then yeah. So that's the theory behind it. Yeah. Yeah, even the what I was mentioning before is that those programming language, because they make your programming so much easier to, so that they are not the fundamental, like the basic language as Java and C++, which you can do a for loop even if it's a n manipulation, 1 billion manipulation. I mean, every CPU is so good, right? So you can do 1 billion computation easily, but it's not also fully because of that. It's because of how they handle memory. Then it becomes really slow if you want to do it, even if it's only 1 billion computations, because of how it handles memory. It becomes extremely slow. Yeah, and that's everywhere. When you do my recommendation for some of the data scientists that you can use for loop in some cases, but try to control the for loop to be less than 100 iterations, so that you don't run into that kind of very slow code. Yeah, this is unfortunately a lot of organizations. I was working with another. I think I was talking to a friend in a bank, right? And then they have a bunch of analysts writing some code, and then their code takes forever to run. And many of the reasons, because I was told they have a 7 nested for loop. Of course, it's going to be very slow. Yeah.
Okay. Do we have any more questions? All right. Let's give our speaker another round of thanks. Thank you very much for this very interesting topic.
Thank you.
All right. Thank you for having me. Yeah.
All right. Thank you. So, all right, I've already posted the link. So if you have any questions afterwards, you can always email your question to me, and I'll see you later. Thank you, Dr. Xie.
Bye.
Bye.
Thank you.